Estember, and my co-authors are Antonio Luis B. Juarez, Jonathan N. Concepcion, and Raymond John Rong S. Zhuang. We are from the School of Industrial Engineering and Engineering Management of Mapua University in Manila, Philippines. My other co-author is Chai Chi Ku, who is currently in from the Department of Industry Management of the National Taiwan University of Science and Technology, Taipei, Taiwan, and previously from the Department of Industrial and Systems Engineering of Chung Yuan Christian University, Taoyuan City, Taiwan. The outline of my presentation will be as follows. I will start with the introduction, then methodology, next will be the results and discussions, and last will be the conclusion. Inventory management plays a vital role in the many organizations since inventories usually contribute to the largest expenses incurred by businesses. For this study, the researchers focus on the following: stochastic demand. So, appearance of stochastic demand presents difficulties in conducting optimal inventory management. Different companies exhibit different demand distributions. Intermittency of demand, which is demand that appears at random with some periods wherein absolutely no demand occurs, is a major concern when it comes to inventory control since it affects greatly the inventory policy of many businesses. Next is the short and long lead times. Lead times is a very important concept of inventory management since longer lead times often lead to very high amount of SKUs. Long and varying lead time often preclude providing the items demanded by direct ordering of the supplier. Next is the high and low cycle service levels. In the field of inventory management, cycle service level or the desired probability of having no demand shortages during a cycle is used in the computation of the reorder point. The reorder point is the inventory level at which the system triggers an order to replenish the inventory. Next is the inaccurate forecast. Concerning demand, forecasting tools are used to predict either the demand occurrences and or size. There are several types of forecasting tools used in forecasting demand, with the simple exponential smoothing being the most prevalent in empirical studies. Other accuracy measure used are mean absolute deviation, the mean absolute percent error, and the mean squared error. Use of the MSE was influenced by several literature which showed that the effectiveness as well as flexibility of the accuracy measure. Next is the lack of downstream forecast information. Downstream forecast information can be defined as the customer's forecast regarding the size of their demand requirements for future periods given their suppliers or to upstream players in the supply chain. The next is the different cost parameters. Priorities may differ when it comes to specific companies' inventory system. A good representation of said priorities are the inventory cost parameters, since this cost represents how much the inventory policy values stocking and stockouts. So some of the costs involved in the inventory are the holding cost, the setup cost, the purchase cost, and the shortage cost. So the gap or the missing information, which was the basis of the study, are the following. This These studies combine forecasting and inventory management in one model, which has not been done in previous researches. Lack of studies concerning application of downstream forecast information and applying control limits to inventory management. In this study, the researchers considered two types of forecasting tools, such as the simple exponential smoothing and the TSB or the Tionter, Synthetus, and Babay, that is modified version specifically designed to handle appearance of intermittent and random demand with some periods wherein absolutely no demand occurs. So this research combines both forecasting and inventory management in a single model. The mentioned forecasting tools are modified such that they include downstream forecast information in their forecast computations and used in the reorder point computation of the inventory management system. The proposed model uses the simple Monte Carlo inventory simulation with allowed back ordering and control limits considerations. The objectives of the study are the following: to model an equation incorporating downstream forecast information in a single item forecasting problem, to integrate forecasting equation in a single level inventory problem, and to show that the proposed model performs better than the earlier classic models. So the methodology works only on the proposed model works only on the following assumptions. There is historical demand for at least the same number of periods that will be simulated. Forecasts provided by downstream tiers are considered in forecasting part of the model. Smoothing constant are computed via Excel solver. The lead time used in simulation is fixed. The ordering quantity for every simulation is fixed. Backlogging is considered. Holding shortage and ordering costs are also provided. Orders arrive on time and are never disrupted. Continuous review system is used for the proposed model. Inclusion of downstream forecast information is incorporated in the proposed model. You can see the forecasting model formulation with the equation using the simple exponential smoothing. Then the equation used by the Cantor, Synthetus, and Babay, which is the TSB model. Then this is the modified formula that the researchers developed with consideration of downstream information. For the model descriptions, you can see the different variables used to develop the model disrupted. This is the formula of the reorder point used by the SES and TSB method. So the first equation is the mean square error computation, and the second is the reorder point. And then these are the control limits used in the proposed model. So you have the control limit, the upper control limit, and the lower control limit. So for the forecasting procedure, so we have developed the procedure from getting historical demand, computing the mean and standard deviation. Then we use the SES using average demand to compute the forecast. Then TSB using average demand to compute the forecast also. Then we also we computed the smooth MSE for every forecast using beta equal to 0.25. Then we calculated the control limits, the lower control limit, the central line, and the upper control limit. Then we also use Monte Carlo simulation. So these are the procedures of the Monte Carlo simulation. For the demand scenarios were generated in a way that it would mimic the demand patterns exhibited by semiconductor products. So we use as case study the semiconductor company. Demand variances for each scenario ranges from a little of 5 million to 6 million to as much as 0 to 10 million. Then the first part of the testing phase consists of 180 simulation runs. Another 180 simulation runs wherein the ordering during the first period would be mandatory. The last part of the testing phase include 1,080 simulation runs. So all in all, we have 1,440 runs. So for the results and discussions, you will find that the TSB showed is best with 50% of the time for the frequency of occurrence with the lowest cost. With the new actual demand for the next 360 runs, it is still the TSB with 73% of the time where the frequency of occurrence with the lowest cost. With the new actual demand and downstream forecast information for the next 360 runs, the TSB still is better for the frequency of occurrence with the lowest cost. And with the new actual demand, downstream forecast information, and new cost for the next 360 runs, it's still the TSB with the highest frequency of occurrence with the lowest cost. So here you will also find the sample graph of inventory position under the control limits. So in conclusion, the proposed model outperforms the classical approach under all conditions. For the first set of 360 runs without the availability of downstream forecast information, TSB method generated the least cost on 180 runs 50% of the time, with SES having 139 runs 38.11%, and classic approach with 89 or 24.72%. For the third set of 360 simulation runs with the availability of downstream forecast information, the TSB method generated the least cost on 290 runs, followed by SES with 170 and classic approach with 28. Thank you very much for listening.